cannot be put in a paper like a single solution. So you have to rely on put that with numbers and make simulations. From the other side of the spectrum, we have statistical mechanics, which is very good and produces meaningful results, but usually they are constrained to system in equilibrium, one, or system extremely large. So in theory, in the limit to the infinite number of particles. So again, very constrained situations where you can get something, but beyond that, in the middle between 3 particles and a finite large number of particles, all that you can expect to do is to put that into numbers and crunching those numbers on a computer. So that is pretty much molecular dynamics today. So a little bit of review about the different variations of this. So, you know, chemists are more familiar with what we call in physics classical molecular dynamics. In chemistry, it's molecular dynamics. It's basically a synonym of that. So at that level, what you have is like a tabulated set of equations or tables for interactions of different particles. Those particles are treated classically, so they are points. And all the nuances of quantum mechanics is hidden in those force fields, basically. On the other side of the spectrum, for physicists, where the electronic structure has something to do, had something to say about it, or quantum chemistry, we avoid having those force fields tabulated, but we compute the forces from solving a quantum mechanical equation. That could be kind of a mean field, like a DFT, using the density for doing that, or actually going into the whole usage of wave functions and all the complications related to that. So 2 words: classical molecular dynamics, able to tackle thousands and millions of atoms, no problem, with the computational capabilities that we have today, and DFT molecular dynamics, which struggles when you go beyond 100, maybe 1,000 atoms. That's as far as we can go today with DFT. So there are a set of good, well-developed, stable and robust set of codes for classical molecular dynamics. So I have here mentioning basically the 3 that we will be mentioning today. And there are also software for visualizing and post-processing those, the results of those simulations. So BND, this one, I found this one recently, very interesting, this Chimera X from, I think it's California, San Francisco, yes, I think it's very good. So you see all those atoms in the ways you depict those for bioinformatics or for biochemistry. Okay, so and here in this paragraph, I basically mention, okay, what you can do in what we call ab initio molecular dynamics. So we are representing the forces, or we are computing the forces from solving a quantum mechanical equation, with some approximation, of course. Nodes that are able to do molecular dynamics are ab init, for example, VASP, Espresso, Octopus, L, Gaussian, for example, for chemists. Are some of those codes. Again, we are at that level, we are restricting in the number of particles that we are able to deal with. So here I am separating those 2 branches, the word again, for fields, what you can do, what are the nuances that are around here. So when you are dealing with biological molecules, The solvents are important, the size of the box that you are imposing, and how, if it's periodic or not, if it grows or not, how you manage the statistical conditions of those systems, if you keep the number of particles fixed or not, volume, pressure, all that is important at that level. In this level, in the level of ab initio, the kind of elements is kind of different. So we are concerned about how many electrons we put in the valence, how many electrons we treat quantum mechanically, and how many electrons we just put in the core, and we kind of mask those. So there are codes like L that treat all the electrons in the system, so that's much heavier. Most other codes just put that, hide most of those core electrons, the electrons that usually have not, in many cases, have not implications for the chemistry of the system, hidden in a pseudo potential, a function that will represent those and makes lighter the weight on those systems. And again, and we will see that in the examples that Nick have prepared for you, the role of optimizing the geometry properly first before you get entering the actual computations, and the kind of things that you do in MVT simulations where you are fixing some of the conditions of the system, and the kind of simulations that you are able to do with that. So two different works. So this is a big range of area and possibilities, and so all that. So now we will go. I think Nick has.
We're popping it over to Kyle, who's going to give you a quick little. Quick little how-to MD, or not how-to MD, but I guess how MD works. I'm
going to give you the bare bones of what this is. So Guillermo covered a lot of the stuff here, so we won't harp on too much. But the big thing to note is that because molecular dynamics assumes initial conditions, you have to have intimate knowledge of how your system is set up. Without that knowledge of like how things should look and how like spacing between atoms and like all the little details here matter, because everything evolves from the initial conditions that you give the program, which in this case is the starting positions of your atoms. So Guillermo talked a little bit about force fields, but since we are dealing with the classical version of molecular dynamics, what we can say that is all of this stuff is based off Newton's second law, where the force of a given system is equal to the change in momentum, which is mass times acceleration. Now, from Newton's second law, we can say that acceleration is equal to the sum of the force on all the particles divided by the total mass of the system. So what we're able to do is that we can use that second equation where Guillermo's mouse is about right now. We can then calculate the force on every atom. And to do this, we do what we've suggested before, is to calculate for each component of the system the force by using a force field. So the force field we're showing here is charm. So if we scroll down, charm has several bonded components. So it's the energy of what these bonds have. So the energy first right there is the harmonic energy of the bond stretching. Then we have the energy of how bonds move for their angles. And then if we calculate the proper adhesion torsion, which is how the two planes interact as they rotate around each other. So if you imagine the sticks there as like two planes that are, they're sometimes perpendicular. If you imagine it's like two sticks rotating at the same time, you get that energy. And then we have the improper energy, which is down there, which is the energy of in and out of phase movement, pretty much. The U-Bradley there term is actually not in every force field. And so we'll skip that for now since it won't be applicable for everyone. And then it leads us to non-bond interactions, which this is like the first chunk of that with the R12. So the distance between the two atoms. That is the van der Waals energy, or the energies of how when two things get close, how they pull and tug on each other. Where the next term added to that is the Coulomb equation. And that's how two charges interact. So all of this combined makes the potential energy surface and the potential energy of the system. And then we can use calculus to, I think the word I want to use is decompose each to its part by using, pretty much we want to break it down into the component vectors. So the X, Y, and Z, if we take the derivative of that potential energy, we get the forces in each direction. And then we can find stuff like total energy and all the properties you see in classical physics, pretty much. That's it, I believe, Guillermo. Oh, my bad. The next thing we'll quickly go and talk about is there's different ensembles. So these ensembles are constraints we put on the system to be able to do the calculation in the first place. The microcanonical ensemble is we constrain the number of atoms in the system, so there's no more atoms coming in and out, the volume and the energy. And stuff for these types of simulations are best for things when either the thing you're measuring is sensitive to temperature, so the change in kinetic energy from being at temperature can fluctuate and screw up your results. Then we have the canonical ensemble, MVT, which is constant number of atoms, constant volume, and constant temperature. Oops. And these simulations, when you run them, what happens is because the volume stays the same, the system density becomes uniform. So everything should be equally spread out while you do an MVT simulation. And then we do the thermal isobaric ensemble, NTP, which is constant number of atoms, constant volume, constant temperature, and I forgot to put in here, constant pressure. So these conditions are what you see in most like wet chem labs. So this is the thing that would directly relate the most to like having something in a beaker. But there are advantages and disadvantages to using each of these assumptions to run your molecular dynamics simulation.
So Nick, do you want to take?
Yeah, I'll start sharing here.
Okay,
yep.
Sure.
So all of that lovely math and intro. Yeah, gotta know where you're coming from here. But I think today we are really trying to focus on one set of tasks here. Yeah, let's say one big goal here. We're looking to take the stuff that we have locally on our computer, and we are looking to take that, put it on the HPC, run things on the HPC effectively, properly. Like Blake said, be a good HPC citizen, all of that jazz. Take it back down from the HPC and look at it a little bit. So I kind of tried to write this to be a one-stop shop on how to do exactly everything I just said, and in that order, so you should be able to start out at the front of this document, work down to the end, and it should show you exactly how to do everything I just detailed. So, okay, well, I guess before that, if you're looking to just listen to me ramble on and not follow along, you can do that if you want. But at least for me, things kind of cement more in my brain whenever I'm doing them along. So if you follow that link, so if you go back here to setup, you can get back to home by just clicking here. You go back to the setup. Thank you, Daniel. Yeah, we are recording. Yes, so should be fine on that. Yeah, so if you click here, you just get back home, go to setup, and then this is a tiny little repo that that we made just to have the code or like the tutorial files that you need to run this on, or run the stuff that we did. So if you download this, should pop into your yeah, save as, download, unzip it, and then that'll have the files that you need there to run. Well, I guess you might unzip it twice because yeah, those are there. But or sorry, yeah, I had a couple different directories that you could use to get your files. Okay. Anyway, let's go back home here. So the first thing that we're going to do here is just pop open VMD real quick. I suppose I'm not going to do it on my computer actually, because I've not gotten VMD to fully work on the Mac. I haven't figured that out. I usually just do things on my computer back at school, but it doesn't have a webcam, so I can't really talk to you on that. But luckily, most things that we're going to be doing, are going to be on the cluster. So all works out here. But if you download those files and in the common directory under the NAMD tutorial files, you'll see ubiquitin waterbox. That's what UBQ WB is. That's what we'll be looking at a lot today. Yeah, if you load it into VMD, you should see something sort of similar to this. You can do that by going File a New Molecule on VMD. Yeah, you'll see something kind of like that. I just put it in ribbons so it would look more visible. All this to just kind of show you, hey, this is what we're going to be simulating. We got a protein in water. This is something that you set up through the NAMD tutorial. Just, one of the first things they have you simulate just to get practice with simulating things. And we're kind of just going to follow along we're going to use the tutorial file, the configuration file that they make there. So you can also see the tutorial that they wrote for that. And we're going to run it here on the HPC. So first thing we're going to do here is, transfer our files here to the HPC using Globus. So Globus is something that WVU pays for, so that we have this excellent tool, excellent convenient way to transfer files to the HPC. So should be able to go here to the Globus homepage. Except I want to open it in a new tab. There we go. Okay, there we go. The Zoom controls are blocking everything. All right. Okay, so should get here to Globus. It says, it's talking about a bunch of stuff we don't care about. But that little button up here, log in. So it should pop you to, if this is your first time using Globus, it'll pop you to a window that asks you what your organization is. And West Virginia University is on there because, like I said, we pay for them. And yeah, it'll go through the same credential authorization that you have for WVU. So if you're already logged in there, then you're good to go. Yes. So I guess everyone give me a quick little. Give me a wave in the chat, or I guess actually, if you have a problem or I'm going too quick, just make sure to let me know this whole thing. Like, I have no idea how long it takes how long it's taking someone to pop into Globus here. So yeah, I guess let me know if you need more time. Raise your hand if you have a question or need help, or you can also also just say you need more time or something in chat if
And
you're
Nick, I
following along
just
with me.
Nick, I just copied I just cloned the repo and put it on a shares folder, share tutorials, so people can just copy from that share folder directly. So just
That's
to
good,
if you want,
but
if you
that
want.
doesn't help. It doesn't help if someone has a PDB locally and they need to put it on the HPC.
Yeah, that's true.
Okay. Thank you, though. Yeah, so once you get on there, for Globus to be able to see your computer, you're going to have to download Globus Connect Personal. Yeah, Globus Connect Personal. It's a little program that you'll need to download. Once again, I'll want you to log in. Also, I keep going over the tab that I need. Yeah, so you can log in, and it really wants to take you back there, doesn't it? Never mind. I take it back. Don't log in. There we go. Right here, it has the different ways that you can install Globus Connect Personal for your different operating systems. So you hit the Mac one, it gives you, since I'm on a Mac, it gives you the thing to download, follow your on-screen instructions, and you should have a little window pops up depending on what operating system you're using. Skip this version. And in Mac, you just end up with this tiny little, yep, right there, tiny little G up in the top, taskbar up at the top here, or menu bar. Okay. So I guess I'm not getting any word from anyone of having problems. So maybe you're just listening and not necessarily following along, which is fine. That's okay. But just gonna keep reiterating, if anyone has problems or I'm going too quickly or I'm skipping past steps, let me know. Okay, yeah. So once you have Globus Connect Personal on whatever computer you're using for, or yeah, that has your PDB and stuff that you downloaded here. Do you need to stay university net, or do you need, no, you do not. Yeah, I'm using it on my laptop and I'm staying in my apartment. So yeah, it'll work even if you're not connected to university or like connected to a university network. You just have to, like I said, use your credentials to log in. And actually, well, you don't need to use your credentials to have the endpoint running, just to actually use the file manager here. Yes, so that's something we're getting to here. So yeah, so you install Globus Connect Personal, and you should now have an endpoint. Mine's named MacBook that you can put up here. The endpoint for Thorny Flat is this right here, WView Thorny, or whatever, # Thorny DTN. That's the endpoint for Thorny. And I tried to make this as, visually, or tried to make the guide very easy to understand without having anyone talk also. So you can go back through and look at it. Yeah, so that's the endpoint for Thorny Flat. That's the endpoint for my MacBook here, or my local computer here. And yeah, let's see, I can go into my downloads. Hey, look, I have a DCD here. So the directory that we want to send our files to here is our Scratch directory. So, yeah, double click on Scratch. This is just like a regular file explorer or finder in Mac. You can just double click on things and move through different folders here. And you can see I already transferred the NAMD tutorial files from this side, but let's send something else here. Like we'll send this DCD over. So to Globe is a little funky sometimes, and I sometimes like transfer things to the wrong spot. So if you have something selected over here, and you have something selected over here, and you hit transfer or hit start, it's going to transfer the file on your left-hand side here into this folder. But if you do this, it'll transfer it into the folder that you are, just the whole folder that you're in here. So it'll end up in my NCF 0003 folder. Yeah, just something to pay attention to, because often I'll end up transferring like a directory inside the directory that I wanted to actually replace with the new directory. So yeah, just something to note. Anyway, so you hit start here, and we will send, we're sending that, or you'd send your directory with all your files in it, like this NAMD tutorial files here. You'd send that to the HPC, and whenever we log on to Thorny Flat, we will see it there waiting for us. Okay. Oh, one other thing to mention here. This is obviously a directory on Thorny Flat here. We scratch and we have users. Very nicely, Globus only lets you see things that you have like the ability to write to. So this is what's called your scratch directory on Thorny Flat. It is basically where you want to run, or where you want to put all your files that you're hoping to run on the supercomputer. So whenever you're doing your transferring, you can always transfer it here. I have things, kind of contained into a couple folders here that's, very descriptive names like replica stuff. Yeah, but keep things in folders. You can have your file system be as nice or as messy as you'd like it to be. Okay. Anyway, so we successfully transferred our files over to Thorny Flat there. So with that done, now all we need to do is connect to the cluster. I guess I say all we need to do. The next thing we need to do is connect to the cluster. All right. So if you, and actually I've just been Googling open on demand WVU, and then I go to Guillermo's page on how to connect to open on demand, and it's this top link right here. Click on that, and boom, here we go. We're in open on demand. So this is the message that you, I think, receive every day, just telling people who aren't allowed in to get out, but you're allowed in, so you're good. And then the thing we want to hit next up here is clusters, and then Thorny Flat shell access. This is going to give us a shell that we can use to talk to Thorny Flat on. And you don't have to have a command line or anything like that. You can just, you don't have to have like a terminal installed on your local machine. You just use this to talk to the supercomputer, which is very convenient. So if we click on that, here we get a new terminal session, and you see we get that same message telling us to get away. But we're here at a command line. Now, I'm not sure how many people who are here have used the command line a lot. I wrote this to, let's see, give a very brief overview of the things you would need to do to get to where we need to go. Very brief. We obviously have a lot more info in something like the HPC Summer Institute has lots of good info on how to use the command line. There's all sorts of things on the internet you can also be Googling for. yeah, but this is just like a very brief of how to get to where we just were. Thank you, Daniel. Very brief, a very brief summary of how to get to where we need to go. So cd scratch, whenever you're doing a bash command, you don't want to copy the first $. That's just people's way of telling you that it's a shell command. So we go back to our terminal here, and we cd scratch. Okay, you'll see that we changed our little squiggle here to be whatever your username is. Should be what it is now after executing that command. Should be all capital scratch with this $sign ahead of it. And after you type it in, cd $sign scratch, you press the enter key and it executes the command for you. Lots of things don't send something back to the command line whenever you execute it. Some things do. This one doesn't. So all of that did is cd is change directory, just moves you from one folder to another. And scratch here is a variable set up by the research computing team that is just a variable to go directly to your scratch directory. So if you execute the command ls, you can see what's in your scratch directory, and you can see the big pile of files that I had back when we were looking at Globus. So this is basically doing the same thing. It's just another way to work through a file system rather than double clicking on stuff. You're CDing and LSing to see what's going on in your directories. So we can see here we have NAMD tutorial files, and that's where we want to go. So let's cd NAMD tutorial files. You can press tab to automatically complete things, which means you never have to type out any giant file names that you make, or I guess say never, but you often won't have to type out giant file names. And then the configuration file, the configuration file for NAMD is inside the 1-3-box directory. And that's where we want to go to run our job. So let's execute that one. You'll see once again, we changed down here. We're in 1-3-box. Now let's do another ls to see what's in here. A bunch of files that I forgot to delete. That's fine, because I can do that right now. And okay, the rest of them can stay there. They're fine. But what should be in yours, if you downloaded it, would be UBQ waterbox equilibration eq.conf. Should have that. That's your configuration file for NAMD, and then the example -output. Those should be the only two things in there. All this other stuff we're going to make by running this. So getting on to running this, let's head back to our thing here. So we're making a PBS script and submitting a job. So PBS script is at least what we call it around the lab. I don't know what everyone else calls it. That's what we use to submit jobs to the supercomputer. So to make ourselves a PBS script, we're going to execute nano, which nano is a text editor. And you'll see what it's going to do here in a second. Nano PBS sh. And if you hit enter, it'll pop you into this file here. This is nano. Welcome. It's it runs it makes a file here called pbs.sh as soon as we save something to it. So what we would like to save to it is this big giant thing right here in the workshop files that I wrote. So you should be able to copy that and then paste it here into your open on demand terminal. And then we're going to go over what these things mean. So here we have our first, let's say like our first block of things right here. This is all information that we're sending to the supercomputer about how we want our job run. These are all different parameters that we're telling the cluster what we want done with our job. And the second block is kind of about software that we're loading and then running our command to actually run NAMD and have it do our job for us. So let's go through these one by one, and we're going to go through them in a little more detail here in a second. So here we have this tells you what queue you're on, or tells the computer what queue you're looking to submit to. We're going to skip that for right now because I'm going to pop out and talk about that in a second here. Here we have, these are email settings. So both, you have your email here that you can have the supercomputer email you whenever your job is finished or has an error. There's another option to have it whenever it begins too, if you want that one. This is just the name of your job. Whenever we run it, you'll see it pop up there, and it's just kind of like a way to have you recognize, oh yeah, that was that's that one. Here we have how many resources we're looking for, or looking to have our job run on. So right now we're just set up to ask for one node, and of course each node has 40 cores on it, and we're looking, so here I'm looking to utilize the whole node. So yeah, if I want to run 2 nodes, I would change this to be 2 instead of 1. And then the last thing here we have is the wall time. So this is how long we're looking for our job to run on the supercomputer. And this can be constrained by what queue you're running on. We'll look at that in a moment here. Yeah, and you just add more zeros to make it longer. So this is 7 days. This is just 10 minutes over here. Yeah, so let's pop out and look at queues for a second. So to leave, you want to hold control, hit X, and it's going to ask you if you want to save. You hit yes, and then press Y, and then press enter. All right, and now whenever you ls, you should see that we have a thing called pbs.sh in there. All right, so different queues. To look at the queues on the supercomputer, you want to execute qstat-q. It's going to pop up this nice list of things here. So there's lots of useful info here. Here we obviously have the queue, the name of the queues. So you saw it standby written in the PBS there. So this was the queue that we're going to be submitting to. This is the queue I submitted that to before whenever I was testing it out. You can see right here where it says wall time. This is the maximum amount of wall time that you can ask for from the queue. So standby is 4 hours. Com small week, that's community. Small memory, and you can submit for a week, 168 hours. Com small day, 24 hours. Yeah, you kind of get the picture there. Yeah, you can also see really only the community queues have time restrictions, but also the community queues are there to be open to everyone. So time restrictions make sense. You know, you don't want someone taking up the whole supercomputer for forever. So really the queues that we kind of only care about for the purpose of NAMD are these right here: standby, com small week, com small day. those are really it. We also, people in the chem department, they'll have access to the chem department queue, which is another good thing here, but we really don't need any of these medium week, medium days. And unless you're in one of these other people's groups, you don't really get access to running on their queues. So, obviously people in Blake's group here, they get to use the JB Mertz queue. I don't know if he opens up to people in class or not. Who knows? Anyway, so yeah, we're looking around standby because our job's not going to take very long. Like like we were doing, we're only requesting 10 minutes. And different queues kind of have different priorities for the HPC. So if your job isn't going to take very long, you kind of might as well submit it to the queue with the smallest wall time, the smallest allowed wall time. So standby here, you can only run for 4 hours. It's kind of where most of the unused nodes sort of go default because they won't be sucked up so long. The whole balancing system of the community queues is very interesting. For instance, if you have not run any jobs this week, you get to kind of jump the line of people who have already run jobs. So let's look over here. So there's 531 jobs queued in the com small day queue. Here's the thing: those 531 jobs, people might have already been running a whole bunch of things for the week. So people are kind of used up like their grace time. So if one of us was to submit to com small day, we'd probably get some time here pretty quick if we haven't run anything on com small day. And it's the same thing with standby, same thing with week. Just kind of all a balancing system to try and make sure everyone gets, kind of a fair crack at the computer and doesn't, it's not being monopolized by one person or one group of people. Okay, so that's all about queues there. Like I said, we're using standby because, well, yeah, once again, we don't need that much time. I think the job runs in about a minute and a half or something. It's not a very long simulation. It's just a nice little tester to get it to run on the supercomputer here. All right, let's see. So that knocks out my talking about queues. All right, and then we start working through the rest of the PBS script we have here. So this is another good piece of info. If you press up on the arrow keys, you can go back to your previously run commands. So pressing up, you can get to nano pbs.sh. We can pop back into that and keep looking at what we have going on here. So after we're done telling the computer everything we want to do with the PBS commands, we start telling it what sort of software we'd like to load. So what we're loading here is a bunch of modules, a bunch of module files. And I'll give you a quick little look by popping out of Nano again. A quick little look of the module system. So these are what are called modules, and they are very like accessible, or sorry, well, yeah, a very accessible way to access all the software on the HPC. Loading them is very easy, and whenever they are loaded, they will add different things to your path, add different things to the path of the nodes, so that you can run different software. Like for instance here, let's load module load. We'll load atomistic. You can also tab complete here, very convenient. NAMD, and then we'll load NAMD get 2021 10.6 MPI. execute that. It tells us a bunch of stuff. And then we should have access to NAMD. So you see we I just typed in NAMD2 and executed it. And of course, it yelled at me for not having a config or anything that it wants. But that's just like a way of testing that you can actually run NAMD. Now, you saw I just ran NAMD off the command line. If you were running it on your computer, you might have been doing something similar, but you do not want to do that here. So this is what we are on right now is called the head node, which is never mind. I was about to make a bad analogy. That would not have gone down a good route. All right. Anyway, sorry. The head node, though, it is it's exclusively for what we're doing right now. You're nanoing some files. You're moving things around, changing directories. You're kind of just talking to the computer. You do not want to run anything on the head node. Very bad. You'll get angry emails from all the HPC people, and probably nice angry emails, or they'll just hit you with like the ban hammer, one of those two. I don't know. Yeah, do not run things on the head node because everyone's here just trying to talk to the computer. You run things on it, you're going to start crashing people's connections, things like that. And yeah, like Blake was talking about, you want to be a good citizen of the HPC and not running things on the head node. Good way to be a good citizen of the HPC. So that's why we're doing all this work to submit a job. But yeah, so this little module that we loaded here, well, runs NAMD. So we can see back in our PBS script that we load a bunch of software. Ooh, I might need to, yep, I'm probably going to make some updates to this a little later. But this will still work for right now. These are a bunch of software that we were loading. Let's see, this PBS script that I kind of pilfered for this, and I was running here. It's kind of wasn't copying. Well, yeah, I guess it was something Blake kind of figured out, and then I adjusted. So this is actually running out of his directory right now, which is he probably doesn't want happening long term, but it works for right now, and that's good enough. And I will update that right after this. Anyway, so this next line here, after we loaded the modules we needed, here we're this is another CD command. We're changing to the directory that we submitted the job from, because the nodes that we get, they don't know where we were. Or they don't know where they should be running the job from. So this is us telling them, hey, go to the directory where we're in. This is just the pathway to Blake's directory where he had the code hidden. And then here we're actually running NAMD, really big compared to just typing in NAMD2, but it's all going to do, it's going to do everything that we need. And then all we need to change here is just our configuration file and our log file to whatever they're named. So you see here we have ubq_wb_eq.conf. And we're setting it to a log file of a similar name. So, okay, that's all of our PBS. I obviously wrote all of it already for you to be good, or for it to work well for us, but you'd have to change a couple things whenever you'd like to use it for your simulations. You'd change the configuration file name, log file name, name of your job, how many nodes you want, your wall time, where you want to submit it to. Everything else would work just fine. So now that we are all done there, Control X to get out of Nano again. And we should be good to go to submit our job. So to do that, yep, Q sub PBS, And we hit enter. That's not good. Unmatched. Okay. Okay.
Nick, have you made the file executable?
You know, nope. Thank you. I was gonna say, I didn't think that was the problem. That chmod would have worked, right? What could have been messed up here?
I don't think that is there. Try a Q sub dash I to enter an interactive to see if that. I think the problem is.
Oh, okay.
Yes.
No.
No, it's entering. No, leave. Okay.
I typed something dumb.
I don't think it matters, does it, if you have the seconds flag missing from your wall time?
No.
Okay.
No.
So I have a question. Why don't you, so like you load it onto the command line module load NAMD, why isn't that under your, why don't you do that in that script?
Very good question. Because the way this is written right now is it's running out of Blake's sorry, a thing that Blake compiled. So that's what this is doing
Gotcha.
here, is that we're actually
Do we
getting
have
a-
access to that folder? Because I don't think I have access to other people's Scratch folders.
Only if you were
No.
in Blake's group.
crap. Well, okay.
Right.
So
But I
I'll be
will-
changing that very quickly.
I will
then.
copy. Yeah, I will copy the module that I'm using for this and put it down in the chat. So this is the
that'd be
module.
great. Thank you.
This is the
Garbo.
module, and this is the command, the equivalent command for running the official. So instead of that MPI run, you run like this. Well, I need to check if the parameters are correct. No, the parameters are correct. I don't. What I need to check is if the parameters are. Oh no, sorry. Optimal. I would no. I would make an. Yeah. Yeah, not optimal, but this works.
Yeah, sorry everyone.
Yeah, that one. I just pasted there.
All right. So
I put 40. It's probably not optimal, but I put 40 plus P 40 and plus PPN 4. I end up using 50 for there. And yeah, that's the model that I'm using.
okay. So
Okay, can you try to submit again? But it does. It's not. That's not yet. That's
Nick,
not yet. It's
oh,
not.
never mind. I would say you still don't have your config file.
yeah, I know.
Yeah, I tried with those things you added in the chat, Guillermo, and it still says unmatched.
Oh yes,
Party.
because I put this UBQB. No, it's there. It's there after the MD.
Oh, right.
So is that the only thing that I have to load? Is this atomistic NAMD? This one you have at the beginning?
Yes, that one, Olivia, that will load all the dependencies, basically, which is basically the Intel compilers, Intel MPI, Intel MKL. So that is one of the options.
Yeah, because I have that. That's the only module I'm loading, and then I have this charm run
Yeah, correct.
line.
Yeah, that's the only thing. IQ sub unmatch.
Yeah, I don't know why it's unmatched. It's weird.
I guess let me check if open on demand's messing up or something. That doesn't make sense. But
That is that could be something that is messing with the Q sub, that terminal. I never use that, so maybe something like that. Because I'm submitting like kind of traditional.
nope, says unmatched for me
Why
on
you
this
don't
terminal.
draw? It's Q sub unmatch. Let me see. I will
Well,
try.
welcome to debugging.
I will try to reproduce what you're doing.
Is there anything that could have gotten messed up from copying?
Just say I've seen stuff mess up from copying before, but you originally wrote it on Mac, right? Because I know we have like a DOS to Unix command that fixes that sometimes, but that wouldn't be relevant to you.
Yeah.
No, the problem is that terminal, that web terminal is the problem. It's not I am getting the same. So on that web terminal, it's a bug on that. I'm trying something.
So are you missing prolog epilogue file?
No, that's not necessary. That's a convenience for checking memory issues but that's not mandatory. Actually, nothing is mandatory in the PBS. So you can put a submission script with nothing, with
Well,
not
yeah,
a
that's
single.
basically what that is.
Let me see if I can get lips. Okay.
Okay.
Yeah, I think I know what it that is. Um,
SMP. Okay, well, I guess I got it running.
Doing what?
I got it running by
What you
well,
did?
yeah,
What you did?
not actually submitting the
Oh, okay.
yeah. I did an interactive job. I got to run that way.
For my reference, what step is this in the NAMD tutorial, Nick?
1.5.
1.5, thank you.
Ubiquitin in a water box. So I can submit jobs, just not that one.
Do you just want to try it interactively, Nick?
I mean, it works interactively. Yeah. All right, yep. Well, I guess just for the sake of plodding along here.
Yes,
Okay.
I got it. Oh, but there is something on your PBS. Yeah, I just copy your file and
It's failing.
it's failing.
Yes.
Wait. So another.
All right, sake of plodding along here. So we can submit an interactive job by running this line right here. So that's what the capital I here flag is for, dash capital I. That's interactive job. And then you can see here, we're actually just using the same things that we were doing in the script. Dash Q is for what queue we're submitting to, so still standby. Dash L is wall time. It's also how many nodes we're asking for, still just one. So we execute that. You'll say waiting for it to start. As it's ready, And then we need to switch directories. So we need to go into, well, I guess we can do the same thing again, CD scratch, and then CD NAMD tutorial files, 1-3-box, back home where we need to be. And then, all right, so we need to load our modules here. So module load, animistic. Thank you, Kyle. Animistic, NAMD, NAMD get 2021, OFI, SMP. Load that. And then we're going to, oh. And then we're going to run Guillermo's line here after sending it to, all right, Speed Racer, just sending it to a log file here, so we don't have to watch all that go across our screen. And then we're gonna hang out for like a minute and a half because that's about all it takes to run. And I guess give Guillermo more time to figure out what's up, maybe.
Yeah, I am working on that.
Yeah, I hear you furiously typing away.
Mm.
Yes. So the last command line, the charm run. Yeah. Okay. So let's see. Explaining it. So explaining it. Let's see. Charm run is what handles the communication between nodes. Well, Guillermo's obviously more or better equipped at dealing with this, but anyway, charm run handles communication between nodes. So not absolutely necessary here whenever we're running on just one node, but if you're running on several nodes, then you'll definitely need it. Let's see, I believe local simply tells that you're looking to run on the resources that are right in front of you here, basically. So you're running on the.
Do you want to follow the idea?
T40 is how many cores you're using. PPN sets another number of processes. And then, well, yeah, that's your config. This is, you're called an AMD. PPN sets a number of processes, and then CPU affinity, I forget what that is for. I think that might auto allocate which CPUs are doing your communication.
It's because I'm oversubscribing that, so I cannot attach.
And this is just sending all of the output from the command to the log file there. Lots of these you can, or yeah, if you want to know more about what all that is, if you go to the NAMD user guide, or no, it'd be the
notes.txt.
Install notes. Whenever their server decides to actually load something. Anyway, it's in the install notes of NAMD how to, or like, yeah, the different ways of trying to run it whenever you're, well, yeah, obviously it's a lot more simple whenever you're just on your local machine, but running it on clusters, there's lots of different options to try and lots of different ways to try to optimize how quickly it runs. I almost feel like, well, Mm. There we go. All right, so I just canceled out of it because it felt like I was going on longer than it should have. All right, so something I like to do is just look at the tail of my log file. Yes, it was actually not even close to finishing. All right, so we might need to get a nice nice optimized version of this command line here out to everyone, just to make sure that we're all running nice and efficiently here. Okay, and in that spirit, let's check out our benchmarking data. Well, yeah, okay. So, well, I have a little section here about checking your job. You can QStat using your username. Obviously, that's a little hard to do whenever you're running an interactive job. You can't see what you're doing, or you know it's actively running whenever it's actively running. And but yeah, whenever you have a job submitted to the queue, you can see here it'll have this output here. You can see your job name, how many nodes you asked for, how long you asked it for it to run, how much time it has run, and this is the status. You can have whether it's queued or canceled or running. Those are the main ones. And then we'll get here into some benchmarking. So to get some quick benchmarking data out of an AMD, it also ends up in the log file here, but we can use grep to pull it out. So let's pop back over to our terminal here, and I'm actually going to exit the node to not suck that up. Okay, and then we can grep capital B benchmark, and then have our log file there at the end. And then when we execute that, we get this info here from benchmarking. Oh yeah, okay. Well, you can see from looking at the ones that I put that I just ran in here earlier today that well, it was running a lot faster before. Here is a days per nanosecond. We usually invert that to show nanoseconds per day. And before I was getting 60 nanoseconds per day on the way I was running it before. Now I can do some quick math here.
This is not very slow.
Basically all I did was I took these the column numbers right here, the days per nanosecond, I averaged them, and then put them over 1, and that gives you nanoseconds per day. Not only is that a good way of knowing how well your simulation's running or how long it's going to take. If you're looking to run it for however many nanoseconds, you can figure out how many days it's going to run. And that's a great way to figure out which queue you want to submit to. So you can run it for a shorter simulation on standby. You just have to restart it more. Or if your simulation you're looking to run isn't actually that long, you just run the whole thing on standby and have it done in your 4-hour window. Or if you feel like messing around with it, you can just submit them all to community week and just wait for them to start up and take as long as they need. You can also figure out how you will scale over several nodes. Okay, so to do that, we would need to run jobs on several different node configurations. So obviously we're running on one node, and that's going to end up being our baseline. This here is a little example of what a benchmarking curve would look like when I made. Yeah, so just running one node here, and then 2, 4, and then 8. You can see I added in this red line. The red line represents perfect scaling. So one node is always going to be perfectly scaled because it always scales perfectly to itself. The one node is basically our baseline. And then, you can make this curve just by saying, oh, okay, well, if one node did, 9.82 seconds, then 2 nodes is going to do double that, and 4 nodes is going to do quadruple that, 8 nodes do octuple that. But obviously, we're not going to have perfect scaling across nodes, unfortunately, because of that's how computers work, basically. And you can see as we kind of get worse scaling as we keep adding on more nodes. They just got to keep talking to each other more and more to.
How many atoms? How many atoms do you have?
But another way you can kind of represent this data is, well, yeah, using the same colors mean the same thing here. Red's still your perfect scaling, so it'd be straight across 100%. This is kind of your efficiency. So this is yeah, so this is like your efficiency. So if you have, obviously you'd be 100% efficient the whole time in a perfect world. But you can see this kind of the ratio of what you did get over what you should have gotten in the perfect world. So really for this, pretend example here, not relating back to what we had. Sorry, yeah, in this example, you probably run 4 nodes if you were looking to, because usually you don't. Crap. Sorry. Usually you want to go below 70 or like 75% efficiency is about where you want to be there. Also, if you ask for too many nodes, it's going to take your job a real long time to start up on the cluster. Just because, the whole balancing act, it'll say, we need to dedicate 8 nodes to you for this long. It's just going to be.
Nick, how many atoms?
Yeah,
Nick?
sorry, it'll just end up being a longer wait to get your job started. 7,051 atoms. Oh, I'm not connected to the sound. Okay. There we go. Okay, now can everyone hear me? Or can I hear everyone? Never mind. Thank you. Yes. Okay, awesome. Sorry, everyone. Sorry, yeah, Blake, in that system, you're talking about me running the stuff I just ran. Yes. That
For your
does
benchmark.
Yes. That does make sense. But yeah, I was getting 60 nanoseconds a day on where I was running on Blake's. So yeah, that was just a big jump for me.
Is the benchmarking data, Nick, your data for a different simulation set?
Everything here and below is different. Right here
How
is
many
what
atoms were
I
in
ran
that
today.
system?
I don't recall.
What?
This output was I just made today. The 60 nanoseconds per day I just got today, running on what Blake compiled. Everything below that is some old from an older system, older run, different times, different places.
If you were getting 9 nanoseconds a day, it was probably about a 40 or 50,000 atom system.
That sounds right. That's normally what I'm running anyway. Yeah, but I guess what I was just thinking, it was weird that this was scaling very well, and what I just ran here is like 10 times as slow. But for the sake of just working through the tutorial here and giving the other guys some time to talk. Whew, all right. The job's probably done. Of course it is, because it was broken. But you get a couple other output files that can be helpful in figuring out problems that you had with your system. Unfortunately, they were not helping us today because we could not even get the job submitted right now. But these two files are automatically created whenever you run a job, and they contain error and output that might come from submitting your job. In terms of running the job, everything else would be caught by the NAMD log file. So unfortunately, no help there, but you already know where to look for that if you know how to run NAMD. Okay. So with that done, we can go back over here to Globus, and we can transfer over our tutorial files, or sorry, yeah, we can transfer over this folder back to our computer here. Remember, again, if you still have it selected over here, you're going to end up putting it inside of itself. So you'll have NAMD tutorial files inside NAMD tutorial files. But if you don't select anything over here or do the little uncheck, it'll end up replacing everything that is the same and adding in the new files that we just created on the supercomputer. Okay, so I just set that to my there we go, downloads, boom. There we go, and we can actually watch it transfer a bunch of stuff over right now. Let's see if I can't actually get VMD running on this bag of bones here. That's not where I want to be.
Nick?
Yep.
Quick question: what information you get from visualizing those atoms in the screen? What you get as a chemist? It's just like curiosity. That's it. What's the purpose of looking at the structure? You know what I mean?
Yes. Well, let's see. Just looking at the structure, kind of as something Kyle was highlighting before. I mean, if you're you should be able to tell if your system looks funky or isn't kind of doing something you expect. I've had several times to visualize my system, and there's a big hole of vacuum in the middle of it. And that's because I didn't properly equilibrate it beforehand. Yeah, so kind of checking out if you have problems with your system. Unfortunately, visualizing this system, it is very simple. So I mean, even if we had a movie version of this, which unfortunately I don't think I can produce on the laptop right now because VMD is being challenging for me. I mean, I guess I could go the roundabout way.
For example, from this image that I'm looking right now, you see that there are not many water ion molecules inside the structure. So
yes, it's definitely
this give you some information about not being properly equilibrated, that kind of information, right? But that's the only thing that I can see, let's say.
Yeah, no, that's definitely a fair observation. Yeah, it being a very simple system, again, yeah, sorry, not too much to look at, but crap. All right. All right, let me pull it up here real quick. That's right. I deleted everything from there. All right, never mind. Forget it. Going back here. Okay. Okay. There's not too many water molecules in here. The problem with visualization for me personally is that I feel that it's pretty easy to get biased by visualizing potentially, because you can say, oh, like, oh man, this really cool weird thing's happening that I think is super interesting, but it's only happening in a certain subset of frames and a certain subset of your simulations, so it's more of an anomaly and less of a like an observable potentially. But and at the same token, that thing that you visualize your simulation for and see as potentially an anomaly, you could do some sort of like numeric like analysis that ends up producing numbers, or it gets you some actual like visible, like some actual data to confirm that the thing that you thought was an anomaly or could have been just like a fluke was actually like an interesting thing that happened or is happening with your system.
Nick, what you call when you use the word
Anomaly.
it means that is something wrong, or is just an event that has a very little probability of occurrence?
I guess I'm thinking more very low probability of occurrence.
Okay.
Because at least the way I end up working is that I'll have 20 different simulations and then 20 different conditions or whatever. So I end up with 400 trajectories. So visualizing 400 trajectories and really trying to get anything really like tangible from them, I think it can be challenging. But like I said, you can also look at a couple and say, oh, there's like this weird thing that's happened. Like, there's an arm sticking out. Let's see how often that arm's sticking out or whatever. You can run some analysis through your trajectory or through overall your trajectories there and see how often that arm is sticking out, sort of thing. Does that make sense, Guillermo?
Mm-hmm.
Okay. So this is a very, very simple tool to use in VMD that will just do an RMSD for you of your structure. So you can open it using VMD, or you open up your trajectory using VMD. Obviously, I wish I could do that for you guys, but I can't. You go to extension, analysis, and then RMSD trajectory tool in the main VMD window. And it pulls up a little window like this, and it defaults to protein because I'm thinking that's what it thinks is actually interesting in your system. And you can select trace here, and it'll go over the course of your trajectory and give you different numbers throughout. And you select plot, and then hit RMSD. It will just produce this nice little plot here that tells you how much you're deviating over the course of the simulation. So you can actually see, you have a little bit of, or the way this is going right now, you have a little bit of change over the course of your trajectory. It's obviously not that much, it's like 3.5 angstroms over all of your over your entire protein, but it's also not a very long simulation, so that kind of makes sense. Okay, and I've taken up the majority of the time, that and the error, and so now I'm gonna popcorn over to let's see, I guess Alex, who's gonna give you a quick rundown on Gromacs.
All right.
And I'll let you screen share, Alex.
It's currently disabled for me. Or did I hit it?
You
Oh,
should
I
be
hit
able to share.
I hit it second too early.
Yeah, I switched it.
Okay, so you can see this. I'm not so used to sharing with Zoom.
We're good
So
out.
I'm doing this my part on Gromacs. It is one of the more common MD simulation engines you will see if you read the papers. This is more this is due to its very high performance, and it's because a lot of force field options, which means it can be used in multiple different areas, as each force field can be basically it needs to be used in a certain way, and it can only be used for certain types of particles in certain environments. So that's not the greatest for explanation of force fields, but basically Gromacs, it can do a lot of things. It's free and it can do it fast, and as I said, it can do more things than it used to with its expansion into non-biological systems. For example, there's been a lot of research into polymers with their studies recently. So to try to save time here, I will not be going over everything as thoroughly as Nick. If something's already covered with Nick, I will be kind of skipping it, going over it. So leave time for Kyle to do his. So one of the benefits with Gromacs is that it's a real simple tool, being able to be used with just all the commands and flags are relatively the same. You start with the GMX, you type the commands you want to do, and then you put in the flags which specify the files you are putting in, and the outputs. And it has a lot of tools which allow it to do multiple things, from setting up the system to running it and doing analysis. So there is a bunch of good tutorials for Gromacs on the website here. It's really quick to get done. However, I'm not going to bother going over that since we are getting a bit close here. But you can get it done like in 5 minutes by yourself, just by following the steps listed on there. It is all command line stuff. You just type in a few stuff, and after downloading downloading lysozyme protein database structure, it is a good tutorial to get an idea of what Gromacs is and how it works. And it has there are other tutorials there for more advanced uses, including more advanced uses of MD in general. So if you are thinking of going a bit more into MD, there are the tutorials there on more advanced techniques, such as umbrella sampling and setting up dummy leads. So it's a good place to look at it. If you want to do this simulation, just the simulation with Gromacs, I have set up the first part of the tutorial here in this zip file. You may want to get it downloaded and follow through. But it's just, it is relatively the same method as the going through the NAMD, other than making sure the setting up the PBS script and in the HPC is the same as with NAMD. You move your files there with the Globus command setup, and once it's there, you move to your directory and go to the file. So it's a very simple to do. After which you can just get the PBS script and qsub it, and it should run. One thing to note, however, while I have set up the PBS script down here, it is important to note that there are many different versions of Gromacs on the HPC. Each one has different effects. Older versions can have different results when running the same system. So it's always a good idea to know what exactly you're trying to do and which version would be best. You can see all the available lists with the module available command. No, I want to save some time for Kyle. So I was planning on doing what Nick did, but to save time, I'm afraid I won't be able to show all the examples. So the module available command will show all of the different modules available on the HPC, and you will then load them with module load. All the information with all the different Gromacs versions start with the authentic Gromacs, and then there's multiple lists. One of the more common types is an MPI version. This is a version of Gromacs specifically set up to run with GPUs to allow faster processing speed. One thing this version of Gromacs does, however, have a different binary initial step. The default version of Gromacs always has the GMX binary at the beginning before the command. However, the MPI versions of Gromacs have GMX_MPI, and it is important to be able to identify which versions are which. So using the command module show, you'll get information on the module, such as what other modules have to be loaded for it to run properly. And by looking at those, you can see if there are any GCC libraries or open MPI software to be loaded. There may be a few others. I can't remember off the top of my head. But if you do see that it's not giving a command not recognized, you would have to just change the command from GMX to GMX MPI or vice versa. So I did mention that Gromacs does require quite a few other modules to be loaded. I don't believe NAMD has the same. It's same, but at times it can have multiple versions of all different versions of Gromacs each have different modules that are required. As such, you would need to use the module show command to get an idea of what is required. Otherwise, if you try to continue using the same ones, same modules loaded for each version of Gromacs, you will end up having the job not run at all. So this is, as I said, this is the PBS script I have set up for this. One thing I did notice that I'm using the community GPU week. While it would probably run quickly for you if you've not used any time on the GPU week queue before, it's probably better to get that changed to standby because this simulation would be a very short one. It took about 5 hours on my laptop, and it would be much faster on the GPU, so you wouldn't have to worry about running it to the wall time. So here would be the commands needed. They are the exact same commands as in the tutorial, just modified with GMX MPI. And one thing I will note about the tutorial is that the MPI versions of Gromacs do not require this flag in the command, which basically tells Gromacs to use GPUs to take care of non-bonded interactions. And that is something the GPUs are really good at, and I would advise doing it, but it is not a required function for the GMX MPI. And there are other things you can tell Gromacs to use the GPUs for, which may or may not be good for your performance. So if you are planning on doing that, it's not required. It's a good idea to find out the best way to get your performance. As Nick said, it's you don't want to be spending time waiting when you can just test it and find out what's the best way to do it. So same as before, the qsub and qsat commands are used to run these run the PBS scripts. I don't know if Nick mentioned that, but the when a job is run, it gives an output of the job name, and it gives both an error and an output where you can see whether an error occurred and how you would be able to fix it, and the output of the commands. They are very helpful for troubleshooting systems that well, they did start running, they quickly crashed. For the Gromacs outputs, they'll be putting out multiple different types of files. Some are specifically for this system's energy, the .edr files. Some are the directory files. Some have all of them in it, but you can choose which files Gromacs puts out. The default systems here are just putting out the default versions with it's specified in the .mdp files. So you can choose what goes out there. Typically it's the TRR, the .xtc, the .edr, and the .logs, along with checkpoints files. So of the ones that are important to look at, however, right now, it would be the .log file. And this has the same information as what Nick was getting from the NAMD, the performance. So it gives the nanoseconds per day and hours per nanosecond at the bottom here. And it also gives the information about how well the nodes are working together a bit above this. I didn't include that in here, but it would be right around here where it tells you how well the nodes are working together in certain tasks. So it's a very good idea to read that. Now, as I'm saying that a lot, aren't I? So the analysis tools that Gromacs has are very useful. They cover a lot of different situations. However, while it does have a viewer itself with the GMX view command, it's not something I use very often. It is not as good as the VMD. So I typically use that, and I wouldn't really be able to give much help for it, but it does give an option in case you don't have access to VMD, but you do have access to Gromacs and you want to visualize your system. And as Nick did go over along with Jeremy, it's always a good idea to visualize your systems to make sure that it does look right. There's a lot of stuff you can do with like graphs and analysis, but you wouldn't really notice stuff that would show that the systems were completely going haywire if you weren't doing any analysis on that. And while looking at the entire system visually over its course of its evolution, you can catch stuff which you would not be able to catch otherwise. So it's always a good idea to visualize them, even if you cannot do them all. So even if you're doing a lot, it's always a good idea to visualize some to get an idea of what's going on, making sure there are no errors in each set series of tests. So as for the analysis command, I'm not going to go over any of them. There are a few mentioned in the tutorial, which are very decent for first-time commands, which are basically getting information on the lysozyme protein. One command I do want to go over is the GMX select command. So most of these commands in using Gromacs also require a .index file at times. This index file basically allows Gromacs to specify which atoms or particles it wants to do the command on. And while it does use, has been programmed to set up the most common groups if there are no index files put in, sometimes that is not enough and the command will just not work otherwise. So it's always a good idea to be able to select which atoms you want. So there are a few different ways to use it. You can basically do the selection in the command line where you can just select the atoms 1 through 1096. This would select the protein. And as I said, it does do available static index groups, such as system and all the other major groups that it has noticed that is in the system. But a lot of the time, this is not working, such as if you just wanted a specific alpha helix of the protein. So you would need to use the GMX select command to then do analysis specifically on that helix. So it is a very good idea to be able to understand that and how it works. It is very simple, but I will will not be able to explain it in the time we have left. So I'm afraid this wasn't nearly as comprehensive as I had hoped, but we are running out of time. Kyle, do you think you would be able to get yours done in the amount of time we have left?
I think it'd be a better use of our time to see, because we covered a lot today. Does anybody have any questions before? Because I don't want to go on if we don't have, like, if there's questions we need answered, let's cover and make sure this stuff is solid so we don't have to move on to another engine.
Do you prefer to not talk about Ember, or because
no,
I
like,
have I have
I'm-
something
it's not that.
I have something to show that could help, that I just prepared for Gromacs. That is the tutorial running on the Jupyter notebooks that could be that is already on the cluster, so I can show that how you can access that and people can follow the tutorials. They are really good. If you want, I can show that, and we skip the Ember.
Well, let's see if anybody has problems with anything before we go on.
It would be
Just
actually
so
cool.
that I have this stuff for Amber, and Amber's pretty simple. All the PBS scripts are in the file of the GitHub file, and they will be on that shared file for at least a little bit. So if you want to run them, or if you have questions, you can contact us. That's no problem. But let's see if anybody has any problems. Like, does anybody have any questions? Like, Jewel, you said you had problems with Alex's.
Yeah, I
script?
have problem in previous script. If you explain the last part of previous script,
This part, Jules?
like GMX, MPI, group, -f. What does is this do?
All right. Yeah, sorry, I didn't explain these. So Gromacs basically has a preprocessor for the well, that's what the PP stands for in the Grom PP. It basically sets up the system to be prepped to be run. It doesn't really take too much time at all, and technically you could run that on a laptop and then transfer the nvt.tpr file, which is basically it's a binary file which system Gromacs will be able to read to be able to run the entire system as long as it has the other files nearby. The GMX MD run command, that is just the basically telling Gromacs to run this simulation that has been set up previously and included in the nvt.tpr file. So what I'm doing is I'm setting up the simulation, putting Gromacs, then running it, and then I'm setting up the next next simulation while using the using a new.nvt file and the output of the previous simulation, and then I'm running it. So I do that twice to get the final simulation running, which is the full production run after going through the two equilibrations. I did skip this a bit, but the .mtp files, those will contain all the information about the simulation, such as the time step, how quickly you want to do, how quickly you want to go through the process simulation, how many different frames to capture per time step, how many steps per frame. I'm really mumbling over myself. Okay. It also has different pressure controls, temperature controls, other end products of the system, which the Gromacs will be applying over the course of the simulation. So of these files here, the .em.grow is basically the system's initial state. The TOFL.top is the force field, the system's topology, all the information about the force field that you want the system to use. And then the .mdp file contains what you want done to the system. And that's all packaged up and put into .tpr file, which then you can run with the MD.
So does it have like config file?
Yes. That is the .mdp file.
.mdp file is similar config like MD, right? NMD.
Yes, they don't cover all the exact same things. I think the namd.config file covers more things than the .mdp, but in general, they are covering the same things.
So if I want to say modify for my system, then especially for my file, so which part should I go for?
What
So
exactly do you want to modify that though?
so say, should I modify like nbd.mdp em.grow?
What exactly are you trying to do to your system though? But that's what I'm
So
asking.
say I generate file from my PSF and PDB, and I have config file, say here is MDP, right?
Mm-hmm.
So I don't know where should I put my file here and what will be the file format.
Okay. The system that is generated, here, I'll go over the steps here. The system that is generated is the .grow file. In this case, this would be, we have the positions of each of the atoms that were and minimized in a previous step in the tutorial. This is, if you change anything about that, you also need to change the resulting information topology. So if, for example, if you went into the .grow file and moved the last 10 waters to make the box a bit smaller and made the box a bit smaller while doing that, you need to go into the topology file to remove the information about those waters. Otherwise, it will get confused having, say, 332 waters in the system rather than 350 that is being told there is. So that will cause it to crash. If you wanted to, however, to change the way that the pressure is being applied to the system, if you want to change the temperature the system's running at, if you want to change the system's time step, that's something you would go into the .mdp file for. This is what contains all this stuff that this Gromacs is applying to the system and how the simulation is being run, other than the force field. The force field is included in the topology file or the .top file. So those
Okay,
are.
so it's similar like say all our topology and parameter file in NMD. So I understand NMD. So if you say something which
I would just want to say, Jewel, I feel like you need just to take a look at the tutorial, and then I feel like more of your questions will be answered. I just feel like you're not familiar enough to like translate
With
one to one.
Gromacs, yeah.
yeah, that's true. I need to look for tutorial.
Yeah, there's some slight differences, but once you do look at the documentation, it becomes a little bit clearer.
Yeah.
Okay.
Yeah, there is if you want to know more about the .mdp file, I forgot to add this, didn't I? There is a large document in the Gromacs manual, which specifies everything that all the different flags that can be put in the .mdp file, such as alterations in the way Gromacs will be doing the non-bonded interactions, changing the cutoff scheme distances, changing how the cutoff scheme works, changing the pressure barostat, and all that other stuff to change the ensembles that the system is using. It's got all that information there. Just type in gromacs.mdp. You'll get that and get a very good idea of what exactly the .mdp file is.
Thank you.
Any others?
You're muted, Nick.
Yeah, I was gonna say, if not, we can have Blake chime in with whatever you'd like to say.
Yeah, I definitely felt like we tried to cram 4 hours worth of material into 2 hours there.
Oh yeah.
Yeah.
And
Yeah.
it wasn't helped by that issue that Nick had.
Yeah, it was not helped. Certainly not.
That's okay. So
The
yeah, I
tutorial-
think hopefully most of you got a good introduction to running MD simulations on the cluster. You know, I think we spent plenty of time trying to talk about even just physically getting your files onto the cluster, but also when you start running your simulations, really understanding how well you're utilizing those resources. And I think it's a little bit more nuanced than sometimes other codes that you might run, like say Gaussian, you know, or some of the other quantum chemical codes, where a lot of times it's just push button and it'll automatically utilize, you know, the number of cores that that you have available to you. But you know, a lot of these skills that we talked about with learning how to read through log files and understanding how your simulations are actually being run is very beneficial. Not only here, but if you ever get to the point where you start to need larger computational resources, like say on Xseed or say Nettles machines here in town, or on other DOE resources like at Oak Ridge. These are all, you know, transferable skills that allow you to run on much larger machines as well. So I think Daniel posted to the chat. There is a link for a survey. I'd really appreciate it if everybody could fill it out. Because for those of you that I don't personally know, I definitely want to take the time to get in touch with you and also follow up with your PIs to see if there's other ways in which we can help facilitate your research on the cluster. And you know, in closing too, I just want to take a moment to thank Guillermo and Daniel and Nick and Kyle and Alex for putting in a lot of time and effort into preparing this today. Very appreciative of it, and I'm hoping we can continue to add on to this documentation so it's more of a living document that people can continue to go back to for help. So anyhow.
Another thing to mention is
Yeah,
we also run office hours every Friday, same time, same Zoom link that you used to get into this one as well. So feel free to stop by. We won't have the expertise of Alex or Kyle there, but me, Guillermo, and sometimes, yeah.
Yeah, well, definitely utilize office hours, but you can also reach out to us any other time as well.
So at what time?
1 to 3 o'clock in the afternoon on Fridays.
Okay.
Same as this workshop.
Yep.